So, welcome to this class on hardware security. So, today we shall be trying to look into like when the fault is affecting the key schedule of a block cipher, and we will be talking with respect to the AES algorithm as we were discussing. So, this is what we will be covering today on how to perform fault attack on AES targeting the key schedule of AES. So, therefore, this is a kind of recapitulation of what happens in a fault attack scenario, in particular in context to differential fault attacks. So, you have got plain text, and this is the normal encryption algorithm, and you get the fault free cipher text. In another scenario, you have got the plain text and you get the faulty cipher text, but remember, right, that you have got the key schedule also which is in play. That means the input key is getting transformed into the round keys by using this key scheduling algorithm. Okay. So, now what we are trying to do is that we are trying to affect the fault, but we are trying to affect the key schedule of AES. Okay. And we know that when the fault is affecting the key schedule, then that would imply intuitively that the round keys will also get affected. And if the round keys are getting affected, when the round key is kind of mixed with the data path, the data path also gets affected. Okay. So, it becomes a more complex scenario where both the data path as well as the keys are getting corrupted. But how do you kind of analyze a block cipher in such a scenario? Okay, because this can be a very practical fault model. Okay. In fact, right, this can be a very serious scenario where you suppose like you have got the keys kind of like calculated at the beginning of a particular encryption, and suppose, right, you basically corrupt the key scheduling at that point. That means the round keys are kind of permanently wrongly like calculated. So, that means, right, as we will see later on, if you are doing something like a comparison based check, right, where you basically compare with the reference, here every time you repeat the encryption you will always get the wrong result. Okay. And therefore, right, that can be quite serious issue. So, therefore, right, faults targeting the key scheduling, right, or key scheduling of any block cipher are a topic which should be carefully investigated. So, let us try to kind of take a look into how the DFA or how DFA has been reported on key schedule in AES. So, this is a recapitulation of how the key schedule works in AES 128, again without loss of generality. So, this is the 8th round, and as you can see that like this is the 8th round key followed by the 9th round key followed by the 10th round key. Okay. So how does this like round transformation work? So, remember that this is suppose like the last column of the 8th round key. So, what you basically do is that you do a subword, that means every byte here is transformed by an S box. Okay. And then you do something which is called as a rote word, which means you do a circular left shift. Okay. So, circular left shift would mean that you basically end up in doing a circular shift like this. Okay. That means, like, this byte gets moved one position, this byte gets moved one position, this byte gets moved one position, and this byte comes to this byte location. Okay. Again, remember, after the S box has been operated. Okay. And then you basically XOR with this column, that means you XOR with this column to give the first column of the 9th round key. The remaining 3 columns are obtained in a much more simple way. What we do is that we kind of XOR this, as you can see, right, we XOR this with this column, that means with this column to get essentially this column, and likewise you XOR this column with this column to get this column, and again you XOR this column with this column to give you this column. Okay. As you can easily understand that because of this, right, the key scheduling was also invertible, because now if I want to obtain this column, and if I am being provided with the 9th round key, then I just need to take an XOR of this column and this column to obtain this column. Okay. Likewise, I will take the XOR of this column and this column to obtain this column, and I will obtain like similarly I can also obtain this column. Okay. Again, for the first column I will do a little bit of trick, because I have to also accommodate this operation, but that is also not very difficult to do. So, therefore, right, we can essentially like this is a reversible process, then therefore from K9 I can obtain K8, and likewise from K10 I can obtain K9. Okay. And that is something that implicitly we have been assuming all through, right. So, now we will be talking about what we can do, right, and in fact, right, there was a paper which was published in 2011 which shows how to use 2 faults on the AES key schedule to recover 96 bits of the AES 128 key. For the remaining key positions, right, it basically had to do a brute force search. Okay. And this attack was essentially due to Kim and Quisquater, and has been essentially kind of shown here. So, this is again actually reported in CARDIS in 2008 apparently, where you take where you consider the AES key, and imagine that like what you do is you kind of corrupt in the first column of the 9th round key schedule. So, as you can see that these 3 bytes are corrupted by corrupted in a random way. Okay. Now, because of the key scheduling of AES, what happens is that this fault propagates, right, and therefore these 3 bytes gets corrupted, and likewise, right, this is how the fault kind of propagates. Okay. Now, if you consider the next key, again, like you will see that all the columns or all the entire round key is now getting corrupted in the 10th round key, and these keys are now basically mixed with the original data path. Okay. So, here you can see that this is the normal data path, but remember that the key has now been corrupted. So, now when we are talking about the differential picture, the differential is not only involving the data path, but also involves the differential in the key. Okay. So, therefore, right, if you want to observe, remember that here when you are because the fault is not in the data path, the differential here in the state matrix is 0, because there is no difference actually. But there is a difference in the key, and that essentially gets manifested in the data path now, and that propagates like is a normal way, and finally, right, the 10th round key comes in, and therefore you get like a distribution which is kind of looks pretty much random in the entire cipher text. Okay. So, now in this particular attack, right, just to summarize, it requires 2 faulty cipher texts to retrieve 12 bytes of the AES key or the AES 10th round key, but there is a brute force search which is required of 2 power of 32, which is still required. Okay, and therefore, right, in this particular attack, you still need to kind of like recover like 4 bytes, and 4 bytes would mean 4 into 8, which is 32. So, therefore, you have to still do a brute force which is of like something like 2 power of 32. And therefore, right, this is not a very I would say an efficient fault attack, and there seems to be a scope of improvement. Okay. More importantly, right, you see that you need faults of this nature, and this is also kind of a restricted fault model, because you need a fault of a specific type. Okay. And it is not a very generic fault model in that sense. Okay. So, now what we will see, or what we will investigate, is how we can do this attack using again like our favorite single byte fault model. And also, right, we will perform the attack with a single faulty cipher text, only with one shot. Okay. So, for that, let us take a look at how what is the type of fault. So, what we will do is that we will again consider the 8th round key rather than the 9th round key, and like we will basically kind of inject the fault in this way. So, we will basically say like take the first column here of the 8th round, and that is this shaded region shows how the fault is affected. Because of the diffusion that I just now said, right, this kind of gets XORed with the next round. Remember that now the key scheduling takes place, the fault kind of propagates here, it again propagates here, and it propagates here. So, now if you consider the further diffusions, right, remember that what will happen over here is that this particular this particular differential, right, will get transformed by the S box. Okay. And then you will be doing a circular shift. Because of the circular shift, this byte will come to this location, and therefore, right, when you now XOR this with this particular column, then the differential will look like this, because like because of this, right, what will happen is that this differential will be 0, but here you will have some non-zero difference, and now when you XOR this with this, you will get a distribution where this is P and this is Q, whereas these 2 differentials are 0. Okay. So, likewise, when you kind of XOR this, right, with this one, then this P and this P will get cancelled out. So, this will be 0 here and 0 and 0. And then when you kind of XOR this with this, you will again get P and Q. So, this kind of will repeat, and therefore, you will get again 0 0 Q here. Okay. So, now when you basically like again carry this in a similar fashion, so again you will see that this Q will now move here because of the circular shift, and therefore, right, you will have something like an R here, and whereas like you will have a 0 which will come down here, and so on, right. So, you will see this will move here, this will move here, and this will move here. So, you will have something like this. Okay. So, now if you take an XOR of this and this, so you will get a P which comes over here, because P XORed with 0 will be P. Likewise, right, this R will propagate here, and you will have Q XORed with 0, so it will be Q. Okay. So, likewise, when you take an XOR with this, then Q and Q will get cancelled. So, you will have 0 here, this will be 0, and you will have P and R. And finally, right, when you XOR this with this, again this will be 0, this is 0, and this is R and Q. And again, when you XOR this, then this Q and this Q will cancel. So, you will have essentially a difference pattern of this type. So, now that would imply that I can now form like some equations as shown here. For example, if you observe the propagation here, okay, so you can see that this Q can be related with this P. For example, if you consider, right, the 8th round key, and you can observe that in one of the cases, right, you have got the actual key. Remember, right, suppose you are considering the key, right, of the, and remember that my key is written in this way, like this is my K00, this is my K01, this is K02, this is K03, okay, this is my K10, K11, K12, K13, right, this is how we have been writing here. So this particular byte, right, is referring to K0 of the K03 of 8, okay. So that is essentially shown here, and likewise if you consider the differential here, then this is K038 XORed with P, okay, because the P is essentially the differential in key. So now if I take the S box here, and then that essentially would give me my this Q differential, and therefore I can write this equation, okay. Remember, because of the invertibility that I showed, this K038 can be obtained by the XORing of the 9th round keys, which are adjacently placed, okay. And likewise, right, for example, you can observe that, so for example, like I know, as I said, right, this particular column, right, can be obtained, right, from this column and from this column by XORing them, okay. And therefore, right, I do an XOR between K039 and K029 to get K038, and likewise continuing this fashion, you can express this in terms of the 10th round keys, okay. So likewise, you can also observe the fault propagation from the 9th round to the 10th round, and then you can essentially form similar equations as shown here, okay. In fact, you know, like I would request you to look into, for example, this column here, like, you know, like how the fault propagates from Q and gets converted into R to obtain this relationship, okay. So for example, remember that when you are considering this particular byte, then this is your, you know, like K33, okay. So in one case you have got K339, in the other case you have got K339 XORed with Q, because Q is the differential, and if we XOR them, then you have got this R, okay. So that is the simplest place where you can get the equation, okay. Likewise, this 9th round keys you can write in terms of the 10th round keys, okay. So that explains you the, you know, like the how you can model the propagation of the fault in the key schedule of AES, okay, of AES 128. So now let us, you know, like see, right, what is the effect of this fault on the propagation of the AES algorithm. So here we take the input 8th round, okay, and remember that I am considering the effect of the fault. So this is my fault propagation I have seen, P, 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 P. So this is written in this way in a horizontal fashion. This is exactly the 9th round differential, and this is the 10th round differential as we have seen, okay. So in particular, we are basically seeing, you know, like the fault, because of this P, 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 P nature, gets propagated here as P, P, P and P, right, and then you have got the sub by shift row and the mixed columns. Because of the mixed columns, now if you observe each of these columns here, so I am showing here one column. This column here has got 2F0, F0, F0 and 3F0, okay. So now you see that this key is also corrupted, and the key right here, this particular differential is P, whereas this differential is Q, okay. So therefore, right, I mean, when you basically kind of XOR them, then what happens is that this byte gets corrupted as 2F0 XOR with P, okay, whereas this byte gets corrupted with 3F0 XOR with Q, whereas these two remains as F0, where F0 is some random byte value, okay. So now if you observe the 10th round, the last round, right, you see that because of the shift rows, this column gets distributed like this, right. So it basically kind of gets spread like this, and now when you are basically bringing in the 10th round key, then you have got here, for example, P, and what matters here is R, because here this differential is 0 and this differential is 0. So these two doesn't matter. You can see that this differential here is 0 and this differential is here is 0, but only here you have got R, okay. So therefore this R gets into the mixed in the XOR, and therefore it also affects this particular byte, okay. So now what you can do is that with this background, right, you can basically what you can do is you can just see, you know, like what happens here. So for example, like this is how the you know, like, so let me just clear this. So this is how your equation looks like. So what we have done is we have basically concentrated on this column, and remember that I am targeting, you know, like say P XORed with a 2F0. So this is your P XORed with 2F0. So I am now, you know, like again working back. That means I am, you know, like going from the cipher text and from the faulty cipher text. Remember, in the correct case I have got K0010, so this is my K0010, okay, whereas in the other case it is K0010 XORed with P, because there is a P which is a differential, okay, and that is why you have got K0010 XORed with P. Likewise, in this case, right, there is no differential, because the other, in this case, as you can see here, there is no differential. So therefore, in this key, both of them are K13, and it is K1310 and K1310 over here. Whereas if you consider this, right, this byte, then there is a differential of R, and that is accommodated here in this equation, okay. And this gives me my F0 and F0. So this turns out for this and this in the differential. And here you have got finally, again no differential, because you are observing this, but then you are basically getting 3F0 XOR with Q. Okay, so this is your 3F0 XOR with Q. So therefore, you can form an equation of this type. Okay. Remember, this is for one key quartet. You can actually form 3 equations for the remaining 3 quartets, because all of them you can similarly form. So if you do that, right, then you will get equations of this nature, and this is how the these are the remaining 3 sets of equations. Okay, as you can see here, these are the 3 sets of equations. Again, I leave it to as an exercise to verify them, but you can similarly derive them. Okay. So now what we would like is, we would like to solve each of these equations, okay, separately, as but if you want to do that, then you see, just like if you try to solve them exactly as we have seen in the DFA context, it is not practically possible. Why? Because if you see each of the equations, there are 4 key quartets, as you can observe here, okay. There is an F1 byte, there is also Q, and there is also R, and there is also P. So there are many variables, and therefore, right, it is difficult, or it at least doesn't look very evident how the the possible values will get reduced, because reduction is very important, right? Otherwise, we will not get a very efficient key recovery mechanism. So therefore, we need to develop a proper divide and conquer strategy by using various equations that we have. So what we try to do is, first we basically try to take the first, second and the fourth equation in each of them. So what we do is, we basically observe that in all these equation sets, okay, in the third equation there is a variable R. Okay, for example, you see that what we observe here is for each of these equations, for example, if you observe, right, then so each of these equations, in the third equation, right, you see that there is an R which is involved. Okay, so therefore what we do is, we basically keep aside these third equations, and we basically, for a given value of P and Q, now P and Q can take 2 power of 16 values. Imagine at this point you are being given a value of P and Q. Okay, so later on we will multiply with this, with all possible values of P's and Q's. So what we do is that we consider the first, the second and the fourth equations of each of these sets. Okay. See, for example, if I consider this set, okay, then you see that the key, right, or then the keys bytes which are involved are K0110, K2310, and sorry, not this one, K0110, K1010, and K3210. Okay, this is essentially shown here, and we know that there are 2 power of 24 possible values here, but then you have got 3 equations, and therefore this has got a probability of 1 by 2 power of 16, which means there are 2 power of 8 possible keys which will survive. Okay. So likewise, you again try this for this set, you get another 3 key bytes, you try this for another, if you combine these 2 things, therefore you will have 2 power of 16 values for these 6 key bytes. Okay. So this 6 key byte is nothing but a union of this list and this list. Okay. So now what we do next is basically, right, we basically try to kind of combine this and see, how we can conjure the key further. Okay. So what we do here is that, in order to develop a further optimization, we basically consider the fault propagation that we have seen. Okay, remember that we had an equation on Q using the 8th round keys and subsequently expressed in according with the 10th round keys. So what we do now is that, using this equation based on the fault propagation in the key schedule, one can reduce the possible choices for these 6 key bytes to because what is the probability that a random, we have already got a value of Q. Go back, right, you see that these keys like K0310, K0110 are already in your set, K03 and K01 are already in your set. Okay, so we have already are there in my set, and therefore, right, what I can do is I will just plug it into this equation and see that whether this set satisfies this equation. And the probability of that being happening is 2 to the power of minus 8. So that means 2 to the power of 16 will be multiplied with 2 to the power of minus 8, and therefore you will have 2 power of 8 values for these 6 key bytes. Okay. Now what you can do is you can again go back to the remaining key set that we have. So we have still like one set that we have not looked into, for example this set, and considered again the first, second and the fourth equations from this set in a similar fashion, and again like obtain finally 2 to the power of 16 values for the 9 key bytes. So remember that here there are 3 additional 3 key bytes. So if we combine with the 6 key bytes that we have obtained, that means we have got in total 9 key bytes. Okay, and the probability that this will basically satisfy this equation, right, is 1 by 2 to the power of 24, and remember, right, you have got 2 to the power 24 3 key byte values. So totally, right, you will have 2 power of 16 values still survive. Okay, so therefore you will have 2 power of 16 values for the 9 key bytes. Okay, and so now what we do now is that we again look into the other equation that we had related to R, and we would like to now go back to the equations that we have left out. Okay, that is the third equations, but in order to do that we need the value of R. So how do we get the value of R? We will use this equation for R. Okay, and we already have, as you can see, like this K3310 and K3210, and therefore, right, we can plug into this equation. We have a value of Q, we obtain the value of R. Okay, and once we obtain the value, once we compute the value of R, what we do is now we look into these 3 equations which we have left out. Okay, remember that in each equation set we have left out one equation. The reason we left out because we didn't know the value of R, but now we know the value of R, so we plug into that, and therefore, right, from the left out equations of each set, keeping the values of F1, F2 and F3 from the previous iterations, because we had a value of F1, F2 and F3, we obtain one value for the key bytes, because like here we will get on an average one value. So therefore you will get one value of K2310, K2010 and K2110. Okay, so therefore what we do now is that with the remaining 2 to the power of 16 values, if you combine them, therefore you will have 2 to the power of 16 values for now. Like you already had like this thing, but now you will be also taking up these 3 additional key bytes. Okay, so now using the remaining set, okay, so remember that we had one equation set which we did not consider. This is the first equation set that we have. So I will now take this equation set and just put it to this and see whether it satisfies. Okay, so therefore we know, right, that from our previous discussions that if you combine with the rest, and considering that there are 2 to the power of 16 values, so therefore now if you combine this, you have got 2 to the power of 8 values for the key quartet. So that means like this particular equation, right, there will be 2 to the power of 8 values which will satisfy this equation, as we have seen traditionally, right, and we can easily follow that. So now what will happen is that if you combine, therefore this 2 to the power of 16 values that you have already obtained will combine with this 2 to the power of 8 values, but again for P and Q there are 2 to the power of 16 values. We assume that I know the value of P and Q, but the P and Q can also take 2 power of 16 values. So if you multiply all of them, you will have 2 power of 40 candidates for the 10th round AES key. Okay, so definitely, right, it's a reduction, but like at the same time, right, I mean it shows that you can actually reduce the key size quite significantly only with one single fault at the input of the or in the 8th round key. Okay, so this is the final equation that we basically observed, and we obtained this 2 power of 40 candidates for the 10th round AES key. So in phase 2, we basically would like to reduce it further, as we have done for like for the DFA on the AES data path. So for that, right, we basically like kind of look into this particular like column of S1, and we see that here we can essentially form similar 4 equations. Okay, so this equation is based upon the fact that all the key bytes that we have here, they are all P. These differences are all P. Okay, so therefore I can again form an equation where P equal to S inverse. Again, remember that I have to go back the inverse mixed column. So this is how it looks like. Okay, I am not you may verify this offline, but you can see that pretty much this means that I am verifying this equation which is P, and likewise this is also P, and this is also P, and this is also P. Okay, so this is just like based upon the fact that you are going back the 10th round and also the 9th round. So you derive them in a similar fashion. Now there are 4 differential equations. Remember, you have the value of P. So therefore, right, the probability of a random like case satisfying this equation is 2 to the power of minus 8 whole power of 4, that is 2 power of minus 32, and here 2 power of 40 keys, therefore 2 power of 8 keys will survive. So again, like just as the DFA on AES data path, you see that with a single fault you are still able to reduce the AES key size to only 2 power of 8 values. Okay, So this essentially essentially explains how you can do the attack, but remember that if you do the attack in this way, then you have to try all the 2 power of 40 keys and you have to do the attack, which means that your time complexity is proportional to 2 power of 40 values. Okay. So you can reduce the key time complexity even further, and therefore you can still reduce it. The question is how. Okay. So for that you have to again take a little bit of look into the equations that you have, and if you carefully observe it, you will find that the following equations, for example, I just show in one of the examples, it actually depends only on 10 key bytes of K10. Okay. So that means I have kind of shown here in the red lines, right? This means that this is the 9th round key and this is suppose the 10th round key. Okay. So what we have shown here is that suppose if you observe this K0210, K1110, K2010 and K3310, right? This essentially shows you the and the other case is K0210, K029, K129, K229 and K329. So I have marked here K02, K12, K22 and K32 of the 9th round key. Remember, this column depends upon these 2 columns of the 10th round. Okay, as I said. And also, right, you also have like K02. So K02 is already covered in the 10th round key. You have got K11, so it is K11 again which is covered. Then you have got K20, which is this key byte, and then you have got K33, for example, which is this key K3. Okay. So if you count, right, there are 10 key bytes which are affected. 4 plus 4 into 2 is 8 plus 2 which is 10. Okay. And in fact, right, if you also account for the fact that you have a P over here, and remember that P and Q are independent, are not independent, there is a dependence, but that dependence depends upon K0310. Okay. If you go back, right, to the equation of between P and Q, then this is how it looks like. So this is your dependence upon P and Q, and then the key byte which is involved is K0310. Okay. So therefore, right, and remember K0110 is already there in my list. Okay. So therefore, right here I have got K0310. Therefore, I have got totally there are 11 key bytes which are essentially crucial here. So therefore, right, we can keep the remaining 5 key bytes which are shown here as constant. Okay. And then you have got 2 power of 35 key bytes, because remember that we have reduced the key size to 2 power of 40 values. So you can split that into 2 parts. In one part there are 2 power of 5 values, which actually doesn't matter for this equation. So you can take 2 power of 35 key values and then they just try to solve them by these equations. Okay. The list gets shortened and it never exceeds 2 power of 35. So at a time, right, you are basically never trying anything more than 2 power of 35, and therefore, right, you are restricting the time complexity which is below 2 power of 35. You do not allow it to exceed beyond 2 power of 35. So that means, right, this attack, right, would be at least like much faster compared to an attack which actually is proportional to a time complexity of 2 power of 40 AES encryptions. Okay. So therefore, the final size of the AES key size is still 2 power of 8, but now the runtime is proportional to 2 power of 35 AES encryptions. So here is kind of a summary of the attack. So you can see that the attack requires 1 fault and reduce the AES key size to 2 power of 8 values, but with 2 power of 35 key conjurings which are required. So if you compare the AES key schedule DFA with the AES data path key DFA, then you can see here that it is like a 2 power of 30, like there is a 2 power of 35 versus 2 power of 30 complexity, whereas like the remaining key size is 2 power of 32 with I mean the result is analogous to the single byte fault induction in the AES 120 data path, where also the remaining key size is 2 power of 32, and actually you can reduce it further to 2 power of 8 values as we have seen. Okay. So you can actually, so here is a minute comment on the optimality of the attack. So here what we try to show here is that imagine that I would like to know whether my fault attack is optimal or not. Okay. So what we can try to do is basically we can try to kind of pretty much guess any values of P and P dash, and imagine that I am trying to create a differential at this point. Okay. So I am trying with like different P and P dash. Okay, and I will try to kind of create a differential at this point, which is essentially nothing but the fault differential that I am like exploiting in a DFA. So imagine that there is a DFA fault attacker who is essentially denoted as this adversary of DFA, and what it does is basically like reduce the key size of AES. Okay, and that essentially is denoted as say KL, which is the key size of AES or key space of AES with respect to a DFA. Okay, and imagine that KS is the key space of AES with respect to classical cryptanalysis. Okay. So remember that, so understand that if, right, I am able to do a DFA attack, okay, and the DFA attack, right, essentially reduces the key size to only KL values. That means, you know, like your DFA K complexity is KL, okay, but how many times you kind of need to do or choose, how many times you need to basically, you know, like choose pairs of plain text so that this difference is created at this point, okay. So this is essentially nothing but 1 by the probability of this delta S, because I am trying to create a delta S differential here, okay, or maybe, you know, like a delta S differential at this point, and that, right, would mean that if the probability of this delta S, you know, is probability of delta S, then I have to try 1 by probability delta S to at least have one case where this differential is created, okay. So therefore, right, if I multiply these two things, then I know that my total key complexity of AES cannot be more than this, okay. Therefore, I can establish a bound where I can write that Ks is lesser than equal to KL into 1 by probability of delta S, okay. Or in other words, I can tell that KL is greater than equal to Ks into probability of delta S. So what is the implication of this? We can easily observe here, if you plug in the values of in the context of AES. For example, in AES, right, we assume that Ks is 2 to the power of 128, and we know that, suppose, you know, like you want a, you know, you basically want a difference distribution, suppose, which is of this nature, okay, a 1 byte difference, okay. So therefore, right, there are totally 2 to the power of 128 possible values, out of which you want a difference of 2 to the power of 8, because this byte can take any possible value, and this is equal to 2 to the power of minus 120. That means if you try 2 to the power of 120 experiments on a random, you would expect that at the input of that round you probably get one such case where you have this kind of difference, okay. And that gives you, you know, probability of delta S, and therefore, you know, like you can expect that KL is equal to 2 to the power of 8, okay. And you can, if you remember now, right, that is exactly what we get in our attack, because we reduce it to the power of 8, and this shows that this is an optimal attack. If you can reduce it further, it kind of hints that you can do a classical cryptanalysis or classical differential analysis of AES, okay, which would be really interesting, okay. So right, I mean, so at this point, right, we basically are done with this discussion, and therefore, right, to conclude, DFA can be applied on AES even more than, you know, like one bytes, or when more than 1 bytes are affected, and that we have discussed in the form of what is called as a diagonal fault attack on AES. And so we have seen that, you know, like even when one of the 4 diagonals of the 8th round is affected, then the final AES key size can be 2 power of 32 with a single fault induction. And DFA can be also performed on AES targeting the AES key schedule, and analysis shows that a single byte fault in the 8th round key can reduce the key size to only 2 power of 8 values with a time complexity of 2 power of 35. Okay. So thank you for your attention.